So let's imagine what happens when we've got a function. Let's call this function f of x. And we know, I'm not giving you the equation of the function, but if we have a point on that function called a, we know the y value is called f of a. And I say, how much would the y value change if I just moved a little bit over? Would it change a lot or a little bit? So really what I'm looking at is if I move just a little bit down the axis, let's make this distance here delta x, change in x, and this would then be a plus delta x, that point. How much would the y value change? Well, the y value would be up here, and if I make a triangle here, this would be delta x, this would be delta y. And I could figure out what my delta y is by, again, putting it into a formula if I was given the function f of x. But I want to talk about this in relation to the linear approximation. So if we now draw a tangent line at that point A, notice the difference between delta y and the tangent line isn't very big. So we're just talking about a little tiny bit here. There's only a small difference. We know that this red line has a slope which is going to be the same as the derivative at a. And I'm going to call this dx. So that means the little tiny bit over, it's called a differential here, dx. And I'm going to call this bit, all of this, from here to up here, dy. So the orange is dy. And notice the delta y and the dy are approximately the same. So I'm going to put approximately here. Are they exactly the same? No. And they're only approximately the same. And the closer, the smaller dx is, the better the approximation. Now, where would we see these kinds of things? We would see this kind of application in error measurements when you're doing a lab. So if you measure the volume of something or the length of something, and there's just a little tiny there's an error uncertainty associated with it, how much of an effect would that have on your final calculation? That's what we're going to be using this for eventually. So the idea here is that for differentials you could use dy instead of delta y as long as the dx is very small. So let's do a specific example now. If I was to have measure the radius of a circle. And let's go over here. So the radius of the circle, really ugly circle there, the radius of the circle is 10 meters. And I'm not sure, I've only got a ruler that will allow it to measure to the nearest 0.1 meters. So really what I'm saying is that it's 10 meters plus or minus 0.1 meter. That's about as sure as I can be. Now that little 0.1 is going to make a difference in the calculation of the area. And I want to know how big that error is. So my formula for area is pi r squared. And I want to calculate the difference that this 0.1 makes. So I'm going to use differentials to do that, which means I'm going to take the derivative, dA by dr, which is 2 pi r. And now I'm going to do something different that you haven't seen before. I'm going to treat this as a ratio, and these are independent variables, and I can think of them as independent variables, and I'm going to move the dr over to the other side. So dA is 2 pi r dr. So that means a small change in r, that's what dr stands for, is going to produce a small change in a. And how big of a change? Well, that depends on how big dr is and how big the radius is. So dA would be, in our case, 2 pi times 1 because times 10 because we've got a radius of 10 meters times the error, which is 0.1, and 2 pi times 1. I'm just multiplying these together, so it's an error, possible error in the area, or a possible difference in the area of 2 pi. Now that is only an approximation. We're assuming the change in area is approximately equal to dA. Why? Because this is very small, which means it's very close to the point 10. I'm just going back. Let's say what we're saying is that if this was 10, then we're only moving a little bit over 10.1 and seeing what would be the difference in the y value. Now that might seem like a lot. This is approximately 6.28. That might seem like a lot. So the next step is, how big is that compared to the area that I would have with 10 meters? So the area would be pi over times 10 squared, which is 100 pi, which is approximately 314. So if I compare 6.28 to 314, it doesn't look so big anymore. And the way I can calculate the relative error would be to figure out what percentage 6.28 is of 3.14. So 6.28 over 3.14 times 100. And if I quickly pick up my calculator here, and 6.28 divided by 314, sorry, not 3.14, I get, that's times 100, which is 2. So it's 2%. So that should have been here. I'm just going to change this so you're not, this is 314. So to calculate the relative error dA over the full area, that's the relative area. So I'm going to do a couple more examples in the next couple of slides.